Now, as we understand this circuit, what we see that we are using a lot bigger components like adder 64-bit. For a 32-bit machines, we need to now think of to have an adder of 64-bit capability, and we need to deal with 64-bit product registers, 64-bit multiplicand storage and stuff like that. Question is, can we do better, like in terms of hardware resource usage? It apparently, if we understand this product process a little deeper, then we'll see that yes, that's possible. Okay, so let's look at this. First of all, shifting is relative. So you are shifting multiplicand to the left side means what? You are doing that with respect to your multiplier, right? You are shifting your position with respect to the multiplier. So instead of doing left shift with respect to the multiplier, while multiplier is at fixed position, it's basically is equivalent to having the multiplier shifted on a right side on one position, right? So shift is always relative. Shift is relative to one fixed point. So with respect to that fixed point, you are shifting left, or you are keeping yourself fixed, and the other reference point in shifting to right is practically the same thing, right? So we actually exploit that observation. So here we are doing left shift by 1, right? So let's look at, initially we had 1010 and 1010, these two, and let's say we have a partial product and product at the end step. So end step product, we want to left shift. Okay, that means we are writing it one left columns. Okay, and in that way, what we are doing on top of the partial product is the LSB of the partial product is being finalizing, right? We are finalizing that bit at this point, because everything else below whatever partial product is will be coming up will be all zeros at this LSB position, right? So we started with, this is, let's say, partial product or the partial sum, whatever you want to call it at this point. We had this, and then at the end step we are doing another product which coming up as 1010, and what we are doing, we are writing it by shifting this nth product, shifting by 1 bit to the left. With doing that, what we are introducing one artificial zero, implicit zero at the LSB side of the product at the end step. And if we go further forward with n plus 1 step, n plus 2 step, n plus 3 step, it doesn't matter what that position summation or LSB position summation is going to be. It will be fixed. It is basically finalized, because down the line everything on that column will be 0, since we are systematically shifting towards the left at each step. So that's what we tell by we are finalizing the partial product bit at this point, and addition is done only the other 4-bit part. So see, we are kind of doing a 4-bit multiplication, but we are trying to keep the addition as a 4-bit, not a 8-bit addition. If we can do it for the 4-bit, then we can apply it for the 32-bit as well. In that case, we don't need to do a 64-bit addition. We should be enough with the 32-bit addition. Okay. So what we are trying to do here now, we get a partial product, we shift to the right, okay, and finalize the bit and add them, the 4-bit, for the next partial product. See, this first page, the operation what we did here by shifting the product nth at the end step towards the left, what we did is same thing if we do the partial product shifted right bit one time, and we finalize the shifted out bit as a final partial product bit, and that way we can keep the summation with a 4 bit for a 4 bit multiplication. So let's apply here. Okay, so we start with the first bit of multiplier, make it this, then right shift both of this partial product and the multiplier together, and we keep the first bit shifted out as a finalized bit, that is represented as a green, and then we do the second, add them as a 4 bit addition, and then now right shift both. See, we are finalizing that 0, one more bit, and then that partial product shift. Then we are finalize 3 of the bit, and we are 0, 0, 1, and then partial product at that point, we add them and shift. Now see, we got our result 0, 1, 0, 0, 1, 0, 0, 0. And that too we achieved by adding up only 4 bit at a time. We no longer need 8 bit addition, we need only 4 bit addition. So here what we do behind the scene, we store multiplicand in 4 bit for a 4 bit example, right? 4 bit multiplication example. We stored them in a 4 bit, but the multiplier and product is stored in 8 bit, which is divided into 4 bit each. Okay, so I'll explain what does it mean. This is a very specific arrangement and special type of hardwares we deploy there. What we are trying to do here, we use the multiplier 4 bit, okay, and product is initialized at all 0 that side, and together it becomes an 8 bit, and I'll store my whole product as a 8 bit between these two 4 bit register. One is initialized and marked as a green, and other is the multiplier bit pattern is loaded, and these two register is a special arrangement between the registers, so that if we right shift these two register, the LSB of this left hand side register will be coming into MSB of the right hand side 4 bit register. Okay, they are in hardware, they are connected in such a way that if we apply shift to the both of these 4 bit register, the left hand side 4 bit registers LSB will be reflected into right hand side 4 bit registers MSB. Okay, so we arrange in the hardware in such a way. So don't worry about to see how that works, but let's just assume this works. Okay, this can be done in the hardware. Okay, we'll see more in the 147 study about how can it be done, but right now just assume this is the functionality you have on the hardware. So what is happening now, we pick up the LSB of the multiplier, which gives us 1, 0, 0, we add them and store this 4 bit addition, okay, not the 8 bit, 4 bit addition onto the left hand side 4 bit register, and then right shift product and multiplier by 1, so that product registers, that 4 bit left hand side registers LSB is came into the multiplier registers MSB. Okay, and the right hand LSB of the multiplier goes out of scope, and then we pick up the LSB again from the multiplier on this position. So then its product is 0, we add them and store it in the product, okay, and then right shift both. So here what you see, what we are doing, we are making the multiplier, since it is going out of scope bit by bit, we are replacing from the MSB side bit by bit with the product, finalized product bit. That's what we are doing. And then we keep on the same thing, right shift, then keep on the same thing, right shift, and voila. Our multiplier went out of the scope and entire 8-bit, like 4-bit per each register. This total 8-bit is my final product. And that's what we do in our optimized circuit here. We stored the multiplicand in 32-bit and we stored the product like 32-bit and multiplier in another 32-bit lower half, and they're kind of connected as I explained that we can actually, this product LSB will come over to the MSB of the multiplier side bit by bit. So as the multiplier goes out of scope, it will be replaced by the finalized bit of the product bit pattern. And we deploy an adder of 32-bit. We don't no longer need a 64-bit addition. And these product multiplier register combinations has common write and the shift write. And this write is basically partially writing into the product term, not the multiplier is never overwrite. It's for the product side, and shift write is applied to both of them. All right, and this product, this 32-bit is going into that as one of the operand of the adder, and other operand is coming from the multiplicand through an 32-bit 2-input AND gate. 32-bit 2-input AND gate. And the other term is basically we are replicating the multiplier 0, the LSB of the multiplier 32-bit. LSB of the multiplier 32-bit. That's what this sign means. We pick up the LSB of the multiplier and replicating, not multiplying, sorry, replicating 32 times. So multiplier LSB, if it is 0, then we are getting 32 zeros in this line. If multiplier LSB is 1, then we are getting all 1 in this line. So as a result, what is output of this AND gate become is we no longer need the multiplexer there. We just know that if we multiply something with 0, it is 0. If we are multiplying something with 1, it is that value, right? So this is perfectly an AND gate definition, and logically it is AND. So if it is multiplied is 0, we are ANDing zeros with the multiplicand bit, and we are getting a 0 for as a partial product computation. If multiplier LSB is 1, then we are getting all 1. Then we are output of this 32-bit 2-input AND gate would be the multiplicand scenario. So we are adding up multiplicand with the product as a partial product calculation. And your controller test is basically go through this algorithm and apply these signal shift right and right at appropriate time, and it runs for the 32 cycle, and once it is done, it says, okay, I'm done. The other outside of this multiplier, whoever want to use that result can pick up the result as a 64-bit. One part, higher part is from the product register, lower part is residing in the multiplier register, where multiplier went out of the scope.